Okay, guys, thanks for joining. So hope you are doing great. And so last, in the last class we have been discussing about the TF. Okay, we just started with the topic called TF, and I think I have given a basic understanding of TF. Okay, the TF is actually for holding the transformation of each frames in a robot. Okay, TF is a library which is an independent library, but it is connected to ROS, and the main application of TF is to hold the transformation of the joints in a robot. You can able to see the transformation of each joints in the robot. Okay, and not only keeping the transformation of the robot, but also like keeping the world coordinate frame. Like I think if you didn't attend the last class, maybe I can show you some example application of TF, so you will get an idea. Just a second, I think I have mentioned that in the notes. Yeah, I think from the notes, yeah, you can able to see this example. So by using TF, we can actually hold all the transformation, all the coordinate frames of an application. Okay, so here is an object pick and place application of a robotic arm. So in order to keep the coordinate frame basically like here there is a world coordinate frame, meaning with respect to the world coordinate frame, okay, the origin of the world coordinate frame is 0 0 0 0 0, and with respect to the world coordinate frame we can say the robot coordinate frame is here, and with respect to the robot coordinate frame the tool frame is here, like that. So it's a series of coordinate frames. Okay, so TF can actually hold these transformation between one coordinate frame and another coordinate frame. Transformation literally means the RCF, if we say the transformation of RCF is with respect to the world coordinate frame, where is RCF? The translation and rotation basically. So with in the x-axis, maybe RCF is like maybe 5 meter, maybe in the y-axis RCF maybe 2 meters, something like that. Like the translation and rotation of a coordinate frame with respect to another frame. Okay, parent frame basically here. So TF basically plays an important role in ROS, basically for holding all this transformation. And why we use this transformation? Because we can able to track all this coordinate frame of the robot, and we can able to like find the object position. So in this example, the application of TF is that there is a camera to detect the object. Okay, imagine, and with respect to the camera we will get the object coordinate frame. Okay, object coordinates basically, and then we have to like convert that coordinate frame or coordinate system into robot coordinate frame. Then only we can pick the object, right? Because if robot doesn't know where is the object with respect to its base, okay, with respect to its base axis, then only the robot can able to pick that object. Okay, currently we only have the coordinate frame or coordinate system with respect to the camera. So using the TF library we can able to transform it, and then we can find the relationship between the RCF and OCF. OCF is object coordinate frame and the RCF. Then only we can initiate a pick and place. So like that, there are many application for TF library. Okay, very important library, and you can see about TF from this IEEE paper. Maybe I can just put the IEEE paper reference here. So this is the IEEE paper of TF. Okay, and today we actually going to see how to program the TF. Okay, yesterday you have seen like how to visualize the TF and how to like play with TF, like using ROS TF tools, how to like check the transform between one frame to another, something like that. Okay. Today we are more focusing on the programming part, how to broadcast a TF, then how to listen to a TF, and then maybe we can start with an example, TF example, that is the turtle TF example. So maybe we can start with that. Okay. So then, yeah, I think that will be good. Just a second. Yeah, this example. Okay, so maybe we can start the class with this example, and then we will be discussing the concept of TF, and then we will start with the programming, all those stuff. Okay. Okay, so so this example, I think I have shown the demo last day. Maybe I can just show you. If you are in front of the computer, you can also simply start this demo. Okay, it's already installed on your computer. So simply copy paste this command. This is actually a launch file. Okay, there is a package called turtle_tf2, and inside that there is a launch file, and this launch file launches the turtle sim and the teleop and the TF application. Okay, so let me simply start this application, so you will get to know like what this example is for. Okay, so here when I launch this application, you can able to see there are two turtles. Okay, two turtles, and in the command line, I can able to move one turtle. Okay, I can teleoperate one turtle. Okay, and when we move the turtle, okay, the second turtle is simply following that turtle. Okay. Okay, so how is this happening? Like actually when one turtle moves, actually when the turtle moves, we will get the position, right? We will get the position of turtle. Okay, and then from that position, maybe another turtle, I mean the second turtle can able to follow the next turtle, I mean the first turtle. Okay, so I mean that will be the method actually for following. Okay, because if I move this turtle, we will get the position of this turtle. Maybe I can show you. So like in order to get the position of the turtle 1, I can simply subscribe to this topic. Okay, you can able to see this topic, and if I move it, the second turtle can listen to this pause, and then it can reach. Okay, but in this project we are actually created this example using TF. Okay, so you will get to know how we can apply TF to your project. Okay, so I just want to show you like how what is the TF tree of this application. Okay, so fundamentally this project is based on TF. So if you load the RQT, okay, and if you load the visualization, that is the TF tree, you can able to see this TF tree. Okay, this TF tree. Okay, so fundamentally, like there is a parent frame called world. Okay, with respect to the world, we have turtle 1 and turtle 2. Okay, so there are two frames, and so turtle 1 is one frame. Okay, and turtle 2 is another frame. Okay, that is actually with respect to the world. Okay, and so what is happening is that maybe we can also see the node graph, so we will get an idea like what is happening in the node level, what are the things happening in this application. So here there are, I think 1 2 3 4 5, there are 6 nodes running. Okay, there are 6 nodes running. This is the computational graph of this application. Okay, this application. Okay, there are 6 nodes running. The sim is basically the turtle sim. Okay, okay, we just renamed the turtle sim node to sim. Okay, and there is a teleop node here. Okay, so when we when we press the arrow key, then the turtle 1 will move. Okay, okay, and there is two turtle, right? So there is turtle 1 and turtle 2. So what is happening is that the turtle 1 TF2 broadcaster program or node, it's actually subscribing to the turtle 1 pose, and turtle 2 TF2 broadcaster basically subscribing to turtle 2 slash pose, and then it is actually publishing what? It is publishing the TF. Okay, so two programs basically publishing TF. Okay, so we will see how to publish TF data and all. And another program called turtle pointer, okay, what it does is that it is actually subscribing, or it is actually listen to that TF. Okay, that is actually publishing by these two nodes, and then this node is sending a command velocity. So what is a command velocity topic? It is turtle 2 command velocity. Okay, so which turtle will move? Turtle 2 will move. Okay, so what is happening is that we are moving the first turtle using the teleop. Okay, so using teleop, turtle 1 will move, and these two nodes, basically the ROS topic node is basically this node. Okay, maybe I can just simply close it. Yeah. Oh, now the structure actually changed. Yeah, this is fine, I think. Or maybe I can start running for explaining easily. Yeah. Anyway, so the turtle sim is subscribing to turtle 1 command velocity from the teleop. Okay, so when we move the robot here using the arrow keys, you can able to see the turtle 1. Turtle 1 is a white one. Okay, that is moving. Okay, so that is actually manual control, and when it moves, there will be a pose topic, right? Pose topic means where is the turtle. Okay, that pose, the XY theta. So there are two turtles. So the pose of two turtle is subscribing by turtle 1 TF2 broadcaster and turtle 2 TF2 broadcaster. TF2 broadcaster means broadcasting means like publishing. Okay, it's publishing the TF, and then that TF is subscribing by or listening by another node called turtle pointer. That is actually moving the second turtle. So that's why the second turtle. So which node is actually moving the second turtle? It is turtle pointer. Okay, and what is the input to this turtle pointer? It is basically the TF. Okay, so this is a working of this application. So if you take any project, or if you run any project, first thing you have to do is you have to visualize the computation graph or node graph, so you will get an idea how the entire system work. Okay, so for doing this simple application, this much nodes and this much topics are working. Okay, and we can only find this thing, or find the working of this complete system by looking the node graph. Okay, and from the TF tree we will get to know like what are the TF topics that is publishing, or TF frames. Okay, TF frames that is currently available, and also you can able to see the TF topic. If you want to see the TF topic, just do the ROS topic list. Okay, and then you can able to see the two topics, that is TF and TF static. Okay, so just echo the TF, and you can able to see the frame ID's world. With respect to the world there is turtle 2, and with respect to the world there is turtle 1. Okay, so world is the parent frame or root frame here. With respect to the world, there is turtle 1 frame and turtle 2 frame. These two frames are moving. Okay, and with respect to the world, turtle 1 transformation is here. Okay, transformation basically the translation and rotation, and turtle to transformation is here. Okay, so basically using this transformation, okay, by listening to this transformation, the node called which node, the turtle pointer, is actually moving the second robot. Okay, so the TF is the main input for moving the second robot. Okay, so that is the this project called the TF example using turtle sim. Okay, so this is one example that we can learn for getting started with TF. Okay, so I think you have seen all these things, and so maybe we can visualize the TF in ROS, so you will get a better understanding. So let me show you the TF of the current application. So what is a fixed frame? The fixed frame will be the root frame. Okay, I mentioned that yesterday, like the TF is having a tree structure. So here the root node or root frame is world. Okay, so in ROS we have to put the parent frame. Here the world is a parent frame, and then in order to visualize TF, simply add TF. Okay, so you can able to see world frame here. Maybe I can simply increase the scale of TF so you can able to see. Yeah. Okay, so let's see what is happening. Okay, so this is a visualization of TF. So you can able to see, yeah, let me simply move the turtle one. See, you can see the TF of turtle 1 is moving, and then the turtle 2 is actually following that. Okay, just a second, guys. Let me close the window, just a second. So I think from the visualization of TF, I think you got an idea, right? Here the world frame and the turtle 1, turtle 2 frame. So when we move the turtle 1 frame, see, the turtle 2 frame is approaching to the turtle 1. Okay, so this is what happening in the TF level. Okay, so we can able to do this project in different ways, but this is one cool example that you can find with TF. Okay, and it's very easy to implement as well. Rather than taking the position of the two turtle, I think working with TF is adding a lot of flexibility in controlling the turtle 2. Okay, so the world frame. So I think maybe I can simply move. Yeah, so this is the world frame actually. We can see. Yeah, so this is 0 0 actually. Okay, so this is the world frame coordinate. Okay, so from this, that is the left bottom. Okay, so this is where the world frame puts, and then with respect to the world frame, the turtles are moving. Okay, so you can able to see the TF visualization. Okay, so if you have any question, you can ask. Okay, or you can simply type. Okay, so I will come to the programming part. Okay, I just show this example. Okay, in order to explain the code of this project, we have to go to the programming part of the TF. Okay, so let me close all this stuff and let's talk about TF programming. Okay, and TF programming is, I mean, it's not a big deal. Basically, I think you all done a basic publisher and subscriber, right? The topic, ROS topic publisher subscriber, maybe using Python or C++ you may have implemented, right? The same concept for TF. Okay, so So I mentioned that TF is actually having a tree structure, right? A tree structure. So the transform between each frames. Okay, maybe I can take this example. So for example, in this application, you can see different uh, coordinate frame, right? World coordinate frame, robot coordinate frame, then tool coordinate frame, and object coordinate frame. Okay, so all these coordinate frame and its transformation. Okay, actually we can publish it or we can broadcast it. Okay, we can broadcast it, and so if we individually broadcast this transformation, the TF library is actually helping us to broadcast actually. Okay, so the TF library help us to broadcast the individual transformation of the robot. Okay, so if you send that broadcast of each frame, like the transformation of world coordinate frame or transformation of robot coordinate frame with respect to the world coordinate frame, we can actually broadcast it. Okay, and all these broadcast you can find it from the TF topic. Okay, so basically the TF topic is actually an aggregate of all the transformation that you are broadcasting. Okay, and from this TF tree we can listen to any transform. Okay, so some nodes are broadcasting the transform, some nodes are listening to this transform. Okay, so in the programming, the TF programming, what you have to know, what you have to know, what you have to do basically is you have to know like how to broadcast a TF, and you have to know how to listen to a TF. Okay, so by listening to TF we can able to like do some application. For example, if you know the transformation between turtle 1 and turtle 2 in the previous application, then you can find the difference between the two turtle, and then we can reduce the error between these two turtle so that one turtle will move closer to another turtle. So application like that we can able to do by listening. Okay, so there are two things. Maybe I can share the tutorials again. So in this tutorial you can able to see in the learning TF session. So the introduction to TF we already discussed. Okay, we will be coming to this project later. Okay, so this project is what we are going to discuss at the end, but you can see here on the learning TF session there is a C++ and Python session. So one example is TF broadcasting, how to publish a transform. Okay, and how to listen to a transform. Transform means there are two frames. Okay, for example, if it is a world frame and turtle 1 frame, so we can listen to the transform between these two frames. Okay, and then how to add a frame. Okay, if you want to add a new frame and publish this transform, you can able to do that. And there is an example for learning about TF and TF time, then time travel with TF. So these are the example that we are going to see. Okay, we will quickly go through it. Okay, and then we will see setting up your robot using TF. That is also basic stuff. Okay, and at the end we will be discussing the example that we have seen, that is this example. Okay, so that is a plan. So first I can go to the TF broadcaster. Okay, so you can also take that example. Okay, I can also like run it. Just a second. Is there any yeah, learning TF? I think there is a package already. Let me see. I think I have downloaded that package from somewhere. Learning TF. Maybe I can download this learning TF ROS package. Yeah, learning TF is here. so that we can simply take this repository for, oh, this is a Python based. Okay. Adding a dynamic frame. Let me check if there is any package available, ready-made package. Okay, there is no package, but maybe we can build it. Okay, so I was just checking if there is an existing package which is having all this example. Doesn't matter, I think it's not available. So maybe we can create a package called learning TF2. Okay, just a dummy package, and we will put all this example for broadcasting and listening. Okay, so just compare with the publisher and listener. Okay, just compare. I mean, it's all that is a concept. Okay, so let's start creating the package. Okay, then we will start explaining the code. Okay, so let me clear the terminal. You can press a Control L to clear the terminal, and then what was our workspace? I think it's Learn ROS workspace. Okay, that is already available. You can just go to your workspace, ROS workspace, and then go to the SRC folder, and then we can create the new package. What is that package? The package is learning TF2. Okay, so they basically given the command to create the package. Okay, so you can simply copy paste this command. So basically we are using catkin create package, which is a command to create a package. Then learning TF2 is the package name, and these all are the dependencies. Okay, so simply copy paste this command and then enter. So we got the new package, which is the learning TF2. Okay, so as a first step, what we are doing is like we can simply build it. Okay, just go to the workspace folder and use the catkin make to build it. Catkin make. So make sure you have sourced this workspace. Okay, so that is pretty important. Just go to the bash.rc folder, bash.rc file, and just go to the bottom of that file and just check you have sourced this thing. Okay, so in the devel folder of the workspace, okay, maybe I can show you. Learn ROS workspace. So there is a devel folder that is creating when we execute catkin make. Inside that there is a setup.bash. Okay, setup.bash, and you have to source. Source means simply running this bash script. Okay, in the .bash.rc. Okay, .bash.rc is basically the configuration file for the bash shell. Okay, so you have to put this command in the .bash.rc. Okay, this is a mandatory thing. And after building it, you can check with the ROS CD learning TF, I think. Yeah. Let me check. Learning TF2. So you can use the ROS CD learning TF2. So that will ensure that this package, that is the learning TF2, is visible. Okay, it's visible in your workspace, and ROS tools can actually detect your package. This is very important. Okay, so if ROS CD can able to detect this package, then what happening is that you will be switching into the package folder. Okay, very important, very useful as well. Okay, so this is a package. Okay, now we can add the TF broadcaster. Okay, so TF broadcaster simply means it will publish the transform between two frames. That is what it's basically doing. Okay, so what I will do is I will copy paste this code. Okay, then I will explain. Okay, so let me copy paste this code. Okay, yes, this is C++ code. So like, okay, so we have to put that. Mostly the convention is we will keep the C++ code in the SRC folder. Okay, it's not a mandatory thing, but mostly like we are keeping the C++ code in SRC, and script folder, inside the script folder we are keeping the Python file. So I'm just creating a new file. We can give the file name as static turtle tf2 broadcaster. Okay, it's a big name, but just a second. Yeah, so this is our code, and I just want to copy this again. Okay, don't worry about the length of the code. I can explain. It's not a big deal. I can explain what is happening. So we have the turtle tf2 broadcaster, and now there is an explanation of that code. Okay, and then they are actually showing how to build it and all. Okay, all the stuff, and then the next stuff is how to write a launch file. Okay, so this is a complete tutorial. I'm just executing it. Okay, so after copying the code, this is a C++ file, right? So we have to add the file name and some functions to compile the C++ code. Okay, so the example is already given. I mean, what to add to the CMake list is given. So simply copy paste, and then what you have to do is just take the CMake list.txt from the package, and then you can clean it. Okay, you can clean it. Otherwise, what you can do is you can simply copy paste these lines at the end of the CMake list. Okay, so it's basically creating the executable from our CPP file. I think you are familiar with these macros: add executable and target link library. Here the executable name is static turtle tf2 broadcaster, and the file name, that is a CPP file, is the static turtle tf2 broadcaster.cpp. Okay, so that's it. I mean, after adding your code, just add these two lines in the CMake list. Now we can able to build the package. Okay, so how to build the package? Using catkinmake. So just go to the workspace folder, which is learn ROS workspace, and then do the catkinmake. So now you can able to see the TF broadcaster is getting built, and we got the executable. Okay, so we have actually compiled the broadcaster program. Now it's actually showing how to how to run this node. Okay, how to run this node. So let me run it. Okay, so in order to run a node, you can use ROS core first, and then the command for running, it's actually given in the tutorial. So just run, just copy paste it, and then let's see what is happening in the RQT. Is there any TF publishing? Okay, yeah, so this is a TF actually currently publishing. There is a world frame, and there is a another frame called my static turtle. Okay, so this TF is publishing by a node called my static tf2 broadcaster. Okay, the node basically the same node that we have run. Okay, this node is actually publishing the TF. Okay, so from this example, did you get anything? Like, did you get any idea about the TF broadcast? I think, like, currently what happened was I just copy pasted a code called TF broadcaster, and then I compiled, I created executable, and then I ran it. Okay, and then I actually got a transformation. Okay, I got a transformation. I got a TF tree, and the parent frame is world, and the child frame is my static turtle. Okay, so this process is actually called the broadcasting of the transform. Okay, broadcasting of the transform. So in the previous example, we have seen a TF tree with world as the parent frame, and then turtle1 and turtle2 as the child frame. Okay, so that is again a broadcasting of the TF. Okay, broadcasting means publishing the TF. Okay, publishing means like we have to like send this transform between two frames. Okay, somehow. So this broadcasting of TF is happening, or it is actually doing by the TF library. TF library is having a set of functions. Okay, you can use that TF library functions to broadcast your own TF. Okay, so if you want to publish a TF, you can use the TF library. Okay, and the same thing for listening or like subscribing. Okay, so you can if you want to listen to the transform between world and my static turtle, you can able to use the TF library API to listen. Okay, okay, so these things will be helpful while working with big robots. The TF is an important stuff. So what happened was like this TF is actually the static, it's a kind of static TF. It's doesn't change, I think. Maybe we can visualize the TF in RVs as well, so we will get a clarity what is happening in the TF. Let me visualize RVs. The parent frame is world, and then I'm just simply visualizing the TF. Okay, so you can able to see the world is the fixed frame, and my static turtle it's actually above the world frame. Okay, with same coordinate x y is the same. I mean it's 0 0, but z value is actually 1. Okay, so this is the transform. Okay, and it's not changing, it's actually not changing, it's static. Okay, so this is the transform broadcasting by the node called static broadcaster. Okay, so the intention of this example is just to show you how to broadcast a TF. Okay, how to broadcast a TF, and you can able to see the code here. This is the code that actually broadcasting this TF, and I can explain the logic. Okay, no need to worry about the length or something. So what is happening is that so we have ran this node, right? We have ran we have ran this node called static turtle TF2 broadcaster. Okay, so this is what we got after compiling the code, this code. Okay, this is a executable that we got. So we actually run ROS run learning TF2, then the node name, and then we are passing some like command line arguments. Okay, one is the child frame name, and also other things are the transform, like translation and rotation. So here x, y, z, and then roll pitch u. Okay, so these are the values that we are giving to the node. So here z value is 1. Okay, so that's why we can see the z value. I mean z axis is like it seems, I mean yeah, we actually put the z values 1, right? So maybe I can put x value as 1 and rest of the value as 0 0. So let's see what is happening in the TF. Okay, oh, okay, just a second. Let me run the node. Okay, just 0. So x equal to 1, y equal to 0, then z equal to 0, roll pitch yaw equal to 0. Okay, let me run it, and then I can visualize it in ROS. Let me change the fixed frame to world, then let me add the TF, and now you can see the world is 1 meter away. I mean, the my static turtle is 1 meter away from the world. Okay, so in ROS we are using the SI coordinate, SI convention, like for distance it is meter, for mass it is kg. Okay, for orientation we are generally using quaternion in order to avoid the gimbal lock. And yeah, so these are the convention that we are using. So what is happening is that we are publishing, or we are broadcasting a transform called my static turtle with respect to a world frame. Okay, with respect to the world frame, and x value is actually 1. Okay, the transform the transform between world and my static turtle is, the translation value is 1, x value, remaining values are 0. Okay, so we can also change the values here. I can simply put y value as 1, z value is 1, and also roll value maybe to orientation. If we are using the orientation in degrees, orientation, it's actually in radians. Okay, so like we can put 1.57 or something like that, and then we can visualize the TF again. So here you can see the TF is here. Okay, in ROS each block or each grid is actually 1 meter. So you can able to see with respect to the world, the my static turtle is 1 meter away in the x-axis, 1 meter away in the y-axis, and also 1 meter high with respect to the z-axis. Okay, and also there is an orientation, there is an angle change. You can see the world frame looks like this, but the my static turtle is slightly rotated, right? Okay, so this is how we are broadcasting a TF. Okay, and now I think I can show you the code, so you will get a clarity. Okay, so here is the C++ code for broadcasting the TF, and in order to write TF based application, TF based code, there are set of header files that we have to include. Okay, we have the ROS.h, that is a mandatory thing for a ROS CPP node, and other than that, in order to broadcast a TF, we have to include transform broadcaster.h. Then in order to include the quaternion functions, we have to include the quaternion.h, then the transform stamp.h. Okay, yesterday we have seen TF is actually a topic which is having the message type as transform stamped. It's an array of transform stamped messages. Okay, transform stamp. Maybe I can show you that. So if you publish a TF, you will get the topic, right? You will get the topic. Currently we are only publishing a static transform. The transform is not changing, so we only have the TF static topic. And if you just check the info of this TF static, you can able to see the message is TF2 messages, TF message. Okay, so this is a message type of TF topic. Okay, so if you just Google it, you can find the TF topic is basically an array of messages, and the array is actually of transformed stamped. Okay, it's an array of transformed stamped, and the transformed stamped message is from the geometry messages package. Okay, transform stamped, or what is transform stamped? The transform stamped is actually having the transform, the frame name, and then the header file. Header is having the timestamp. Okay, so each transform stamped value is having a transform of the child. For example, we have transform of turtle 1 and turtle 2. Okay, so here the child frame ID will be one child frame ID will be turtle 1, and the transform of the turtle 1 with respect to the world will be storing in this value. Okay, in this value, and the header will be there, and another child frame is turtle 2. Okay, so like that it is actually storing an array of transforms. Okay, so if you check the TF2 broadcaster, the TF2 broadcaster is actually publishing or sending an array of the transform stamped messages. Okay, so this topic or this node, basically what it does is that it is actually like receiving some command line arguments, including the child frame, then the transform. Okay, transform basically the translation and rotation. Okay, so as the command line argument. Okay, so here you can able to see in the main function we are getting the child frame name from the command line argument, that is RGV. Okay, I think you are familiar with this command line argument, RGC and RGV. So we get the child name, frame name from RGV1, and after that the translation, rotation, all these values are coming from the command line argument. Okay, so when we execute the node, I think you may observe we are passing the child frame. Okay, child frame means with respect to the world is the parent frame. Okay, that is actually fixed. With respect to the world frame, we are publishing this child frame, and the transform of the frame is this, the translation and rotation basically. Okay, so you can able to see the how we are like broadcasting the TF. This is a section basically doing that job. Okay, this is a section that is mainly doing that job. Okay, so the main function is the main class that is using for broadcasting the TF is called the this one, static transform broadcaster. Okay, broadcast, this is actually a class inside this header file. Okay, and we are creating an object of that static transform broadcaster, and then using this static broadcaster we are actually publishing the TF. Okay, we are actually sending the TF. And what is the message type of TF topic? It is transform stamped, right? So we are creating a message called static transform stamp. Okay, so the message type is geometry messages transform stamp, and this is a message, okay, that we are going to send. Then we are basically filling this message. Okay, so in this message we are filling with the timestamp. Okay, so in order to get the timestamp we can use ROS time, and we have to fill it with the parent frame ID. Okay, that is actually the frame ID refers to. So the frame ID, what is the frame ID? The root frame is a world, right? So we are giving world, and then what was the child frame ID, which is the turtle name. Okay, static turtle name was the child frame. So we have to fill that, and then we are filling the translation from the command line argument, x, y, z we are filling, and then the TF only accepting the quaternion value, right? But we are giving the roll pitchio value, right? So there is a function in TF library in order to convert the the Euler angle into the quaternion. Okay, so this is a function like it's not actually a function, but like there is a class called quaternion, and we are creating an object of the quaternion, and there is a function inside that class called set rpi. Okay, so what it does is that it is actually reading from the roll picture and converting into quaternion. Okay, quaternion. So quat will be having the quaternion value. Okay, and that quaternion value is actually filling in the rotation part. Okay, so we are actually filling the other element, and you may have some confusion like how will I get to know these elements. So basically just go to the geometry message transform stamped. Okay, just Google about this, and you can see what is inside the geometry message transform stamp. Okay, we have the header, we have the child frame ID, we have the transform. Okay, so inside the transform you can see translation and rotation. Inside the translation, each translation is a float value which is having XYZ. Okay, so that is what we are basically feed to this message. Okay, and then after filling the static transformed message, what we are doing is we have a function called send transform. Okay, send transform. So this is a broadcaster object, and inside the broadcaster object there is a function called send transform, and then we are just passing this message to the send transform. Okay, so you can compare this with the ROS topic publisher. Okay, in the ROS topic publisher, what happened was we have a message to send, right? So it may be string, it may be an integer, right? So you have to fill that message, and then we have to publish it. Okay, similar to that, we have to publish the transform. Okay, for that we have to fill the transform stamp message, and using the broadcaster object, which is similar to the publisher. Okay, we are sending the transform. Okay, so after that it is simply waiting using the row spin function. Okay, so this is how the transform broadcast is working. Okay, so let me know if you have any question in the transform. I think you got the logic, right? We are creating the broadcaster object, we are creating the TF message and filling with the values, and then we are sending the TF. Okay, so no need to worry about the TF topic name and all. These broadcaster is actually sending the transform to the TF topic only. Okay, if it is a static, then it will be going to the TF static. If it is a moving one, then it will be going to the TF topic. Okay, so I think you got an idea, but let me know if you have any question, because it will take some time to digest. Okay, it's not very easy. You should like practice all this stuff. Okay, so let me know if you have any question. The TF broadcaster example, I have used the same example that is mentioned in the ROS tutorial, so that will be useful for you as well, because if you follow this example, you can listen to my my lectures. Okay, so let me know if you have any question, guys. Okay, you can simply comment, or yeah, if you have any question you can ask. Okay, yeah, so now I think we can go with TF2 broadcaster. So the first example was static broadcaster, and the second example was TF2 broadcaster. So the difference is that the static broadcaster simply publishes static transform. Okay, that transform doesn't change, but the TF2 broadcaster, what it does is that it's actually sending a transform which is actually changing. Okay, so maybe I can show you the example of this code. I mean, I can show you the working of this code, and then we can start explaining. Okay, so this is actually the, I think this is the project code basically. I think we have seen that project, right? One turtle is following another turtle. So this is actually the source code of that. Yeah, it's actually the source code of that node. Yeah, yes. No, not the complete code. I think the TF broadcasting. Yeah. So what I'm doing is I'm simply copy pasting this code first, or simply create a new file using gedit, and then I'm saving it in the learning ROS workspace. Okay, so this is a folder, and I'm giving the name. The name of the CPP file is turtle tf2 broadcaster, and now I'm just giving it. Okay, so this is our source code, and now I'm just copy pasting the code. Okay, and now copy pasting to the file. Okay, now we have to compile it, right? We have to compile it. So adding the executable target link library, just copy paste into CMake, open cmake.list, and then at the end just add this. Okay, so that's it. Okay, so just understand how to compile a CPP node. Okay, just add to the src folder and add these 2 lines. Okay, now we can compile it. Compile and build using catkin make. Okay, so it is building. Yes, it's actually builded the turtle tf2 broadcaster. Okay, and now they actually showing a launch file to start these nodes. So I can explain that. Before that, I just want to show, maybe I can start the launch file, so you will get a better understanding. After that, I will switch to the code. So they are putting a launch file in the web page. So what I'm doing is I'm just going to the package called learning tf2, and then I'm creating the launch folder for keeping the launch files, and then I'm creating a launch file called what was a start demo.launch. Okay, start demo.launch, start demo.launch, and then I'm simply copy pasting the launch file that they have mentioned. It's an XML type, so marking as XML. And then what is happening? Yeah, turtle1, yes. Okay, so now I'm starting this launch file. So before starting the launch file, just go to the launch folder. Oh, it didn't saved. Oh, okay. It's actually saved in the folder. Yeah, so it's actually saved in the package name. I'm just moving into the launch folder. Okay. So just go to the launch folder and change the permission using chmod. Okay, you can make that launch file as executable. Okay, this is just for the visibility of the launch file. Okay, using chmod. So after changing the permission, you can see the green color. Okay, so now what I'm doing is I'm launching this launch file. So launch file can be launched in 2 ways. The actual way is first we have to mention the ROS launch command, and then you have to mention the package name. Okay, package name. and then you have to mention the launch file. So after mentioning the package name, give a space and then press the tab twice, then it will be auto completed. Okay, so now you can able to see the node running. Other way of running the launch file is just ROS launch space start demo dot launch. Okay, but for this you have to be in the launch folder. Okay, so that you have to taken care. But I will prefer this command, which is ROS launch space package name space the launch file name. Okay, so I'm just starting it, and then I am taking the RQT, and then let me see the broadcast. Okay, so the Turtle1 world to Turtle1 broadcast is here. Let me see if there is any other things. Okay, Turtle1 and Turtle2. Okay, so let me start. Okay, so we can able to see when we start the turtle sim, we can able to see the Turtle1, right? So I just want to start the Turtle2. So in order to create a new turtle, what we have to do is we have to use the spawn service. Okay, spawn service. So just use the spawn service and just give the name as Turtle2, and then just give some value for the initial position of spawning. Okay, so now we can able to see two turtles, and then if you check it, you can able to see the transform of two turtle. Okay, two turtle, and you can able to see the transform of two turtle is broadcasting by a node called Turtle2TF broadcaster. Okay, so what is happening is that when we run the launch file, okay, the launch file actually started some nodes in order to broadcast the transformation of two turtles. Okay, so this is what actually happened. Okay, and maybe we can take the broadcaster code for better understanding. So we are taking the Turtle2TF broadcaster. So what is happening in this code is it's very similar to the last code that we have seen. In this code, what is happening is that it is actually subscribing to what? The pose of the turtle. Okay, it is subscribing to the pose of the turtle. So there are two turtles, and Turtle1 and Turtle2. So we will get the position of Turtle1 from the topic called Turtle1/pose, and we will get the pose of Turtle2 from Turtle2/pose. Okay, so this node is basically like listening or subscribing to which turtle that we are giving. Okay, so if it is Turtle1, it will be subscribing to Turtle1/pose. Okay, and when it is subscribing, and if there is any data comes to this pose topic, it will call the pose callback, which is actually this. Okay, this is the pose callback. Okay, so the pose of the Turtle1 or Turtle2, okay, which turtle that we are putting here, we will get the pose, and then that pose is actually broadcasting. Okay, that pose is actually broadcasting. How we can broadcast? Like the same steps. Okay, so in order to broadcast a moving TF, we have to use transform broadcaster class. Okay, so transform broadcaster class we have to include. If you want to publish a static transform, Then static transform broadcaster, if we want to broadcast a moving transform, then we have to use the transform broadcaster. So the transform broadcaster will publish the transform in TF topic. Okay, the static transform broadcaster will publish the topic in TF static. Okay, so and other stuff is the same, like we have the transform stamped message, and what you have to do is you have to fill that message. Okay, you have to fill the time, you have to fill the fixed frame or the parent frame, that is world, and you have to give the child frame, that is the turtle1 here. Okay, turtle1 or turtle2, anything can. And then we are giving the translation value, okay, from the pose. Okay, from the turtle pose topic, we will get the translation of the turtle and also the theta value, the rotation. So what we are doing is we are actually giving the translation value to the transform stamped message, x and y. There is no z value because the robot moving in a plane. And then we have the theta value, right? From the message we will get x and y and theta, right? So I think you know this, right? If you just echo turtle 1/pose, you can see we will get x, y and theta. Okay, basically we will get that. Also we get linear and angular velocity, but we are only taking x and y for x, y, theta for the transformation. So x, y, and then we are setting we are converting the theta value into quaternion. Okay, so the theta is actually the yaw value. So roll pitch is 0, and we are feeding the theta value as yaw, and it is getting converted into quaternion, and that quaternion is feeding here. Okay, and then it is publishing, or it is sending the broadcast. Okay, so the same node can be used for broadcasting the TF of turtle1 and turtle2, or any number of turtle. Okay, so that is what we have seen in the launch file. Okay, in the launch file you can see first we are starting the turtle sim. Okay, and then we are starting the teleop turtle. Okay, so that we can move one turtle, and then we are actually setting some parameters in order to speed up the movement of the robot. Okay, and now this is what we are starting for sending the broadcasting. Okay, so here what we are doing is we are starting the turtle TF2 broadcaster with command line argument turtle1. Okay, and we are starting the same node with command line argument turtle2. Okay, we are also changing the name of the broadcasting. Okay, this name means name of the node. Okay, so one node will be turtle1 TF2 broadcaster, next node will be turtle2 broadcaster. So you may have some confusion, like the same program. Okay, same executable but two instances. Okay, so that is what happening here. Okay, so two nodes, same executable. Okay, same program. We have the executable of this code, but we are running the same executable two times with two names. Okay, so let's start this launch file. Okay, let's start this launch file. I think it's already started. Maybe I can. Okay, so now we can able to see the turtle, and then I can show you the computational graph. Okay, so this is the computational graph, but initially when we start we can only see one turtle, right? But we have to start the next turtle manually. Okay, so maybe I can do that, because the code expecting two turtles. Okay, so I'm simply calling the spawn service for the turtle2, for creating the turtle2. So 3 3. Okay, so there are two turtles, and now if you check the RQT, if you check the TF tree, you can see this. Just a second. I think this will be fine. Yeah. So here the sim is the turtle sim. The teleop is the teleop node. So which will move the turtle one, and then the sim, the turtle sim is publishing the post value, right? That is actually subscribing by the broadcaster. Okay. So this is actually the part of the project. Okay, I think we have seen that project, right? So this is actually the part of the project. So this part will be basically publishing what? Publishing the transform of each turtle. Okay, and we can able to see, and there is a final node which is actually listen to this TF, and also we can able to see that ROS topic list, ROS topic echo TF. You can see the TF data is getting published. Okay, and maybe I can also show you yeah, I can simply move the turtle 1. Okay, but the turtle 2 will not follow, because there is a follow node which is actually taking turtle 1 and turtle 2 frame, and then it is trying to reduce the error between these two, but that is not currently running. Okay, so maybe what I can do is I can visualize the TF in ROS. Just a second. Is there any other nodes running? No, right? Yeah, let me take the ROS again. Right, I'm putting world as the fixed frame and then taking TF. Okay, so now you can able to see the two frames. Okay, the world frame, turtle 2 and turtle 1. Currently we are only moving the turtle 1. Okay, you can see I'm just moving the turtle using the keyboard teleo. Okay, so the TF, it's a moving TF, right? So it can be visualized. Okay, okay, so this is the first part of the project. Okay, like publishing the transform of each turtle. Okay, then there is another code which is actually coming. I don't think we can complete that. That is in the listener code. Okay, so the listener code is actually listen to turtle transform, and then it is publishing necessary control commands. Okay, so I think maybe next week we can just complete this project. Okay, you can also go through the code. So after that, I mean, after completing, we can go through these two tutorials. Okay, then we can jump into the next topic. Okay, so I think that's for today. So we can do a Q&A for today's example. I know it's slightly difficult because there are a lot of information. The code is also not very easy to understand, but maybe you can ask any questions. Okay, just understand the logic. That is what the importance is, and all the information of this tutorial and everything is available in the ROS wiki. Okay, so I was just like giving some I mean idea. Okay, so if you start understanding, I mean, everything from ROS wiki, then it will be okay. But in the beginning, it will not be like that. It will take some time to get used to with the ROS wiki. Okay, So let me know if you have any question, guys. Today we have discussed about mainly we have discussed about the broadcasting of TF and yeah, broadcasting basically. Okay, so the objective of today's session was like explaining this project. Okay, that is called TF demo, and we have seen one part of the project, which is publishing or broadcasting the TF. Okay, the next part is listening to this TF and then giving the control commands to turtle 2. Then the turtle 2 will follow the turtle 1. Okay, so let me know if you have any questions. Okay, so next class I think I can also show you how the Python code works. Okay, there are two versions, like the code will work with, I mean, the TF libraries for available for Python and C++. Okay, so the same code is available. The code length in Python is very less. Okay, but I will prefer you to stick on to C++, and you can, I mean, if you know C++, then you can quickly adapt. Okay, so let me know if you have any question, guys. Any questions? Any question, guys? Okay, so if you don't have any questions, I think we can conclude today's session. Okay, so next session will be on next week, and we will be completing this project by explaining the listener and this thing. Okay, so then you will get an clarity. Okay, I will also show you some existing projects, okay, using TurtleSim, and then after that we will be jumping into URDF. Okay, URDF. So yes, so that's it, guys. Thanks for attending. See you next week. Bye.